Okay, now we move on to the next session again on exercise 6 memory segmentation. First thing is, how do we implement protection? I am going to read out these 4 points very slowly and I will read it out twice. By the time you will also understand what it is. Okay. Every segment is associated with a descriptor stored inside a descriptor table. This we have explained. I hope there is no doubt. Again I repeat, every segment which is going to be created in the memory will be associated with one descriptor stored in a descriptor table, and the privilege level of any segment is also stored in its descriptor. Now by these two statements what happens is, every location in your RAM has a privilege level associated with it, correct, because every location in your RAM is associated with a segment here and every segment has a privilege level. This essentially implies that every usable segment or every segment in your RAM that is currently being used is already associated with a privilege level. So like this I can get a very low granular, fine granular privileges assigned. So every byte in your memory I am in a position to assign a privilege level through this mechanism. Now this entire bunch of descriptors are maintained in the memory itself in a descriptor table, and the start of this descriptor table, where will the descriptor table start, that is stored in a register called descriptor table register, right, because when I say selector number 5 means I say go and get the 5th selector in your descriptor table. I should know where the descriptor table is starting, then only I can go to the 5th entry in that and pick up. So where will I know where the descriptor table is starting? In what you call as the descriptor table register. And the segment register, what does it store? It stores an offset into this table. So the segment register only selects the descriptor, correct. So the segment register is also called a segment selector. Got this? Now when we look at the global picture, you will understand why this level of complication, or if at all you feel it is complex, why this level of complication is necessary. Okay. Now there are two descriptor tables, one is a global descriptor table, another is a local descriptor table. Already we had some discussion on why we need a global descriptor table, why we need a local descriptor table, but we will elaborate on this as we go. So if I have a global descriptor table, I have a local descriptor table, there should be registers which point to the start of the global descriptor table, there should be register that points to the start of the local descriptor table. So essentially I have two registers, GDTR, which is global descriptor table register, and LDTR, which is local descriptor table register. For our understanding, there is one global descriptor table which is used by the operating system. So the GDTR will point to that table. As and when a process is created, a local descriptor table is created for it. So every time a new process is created, the LDTR will be changed to point to that local descriptor table. So let us say you two are two processes, process 1 has its local descriptor table at 5000, process 2 has local descriptor table at 10,000. When you are executing, the LDTR will point, the value of the LDTR will be 5000, when you are executing the value of LDTR will be 10,000, right. Now how will I load into this GDTR and LDTR? Please note, we are building the security very slowly. How do I load the value into this LDTR, GDTR? I have to load 1000, I have to load 5000. So I use two instructions, namely load global descriptor table register which is called LGDT, and load local descriptor table LLDT. I use two instructions, namely LGDT and LLDT. Okay. Now, please note, this is very important. The LGDT and the LLDT instructions are privileged instructions. That means only a code executing in privilege level 0, in our case the operating system, has the permission to basically load into this global descriptor table, load into this local descriptor table. A privilege level 3 code cannot load into the global descriptor table. A privilege level 3 code cannot load into the local descriptor table register. So, when I want to create a GDT, who can create this GDT? Only a privilege level 0 code can create it. For the simple reason, because the base address for this LDT or the base address for this GDT can be loaded only by the privilege level 0 code, because we have to use these two instructions LLDT and LGDT to load into those registers, and that two instructions LGDT and LLDT are what? Privileged instructions, and they can be executed by only privilege level 0 code, and so nobody other than the operating system can create a GDT or an LDT. Even if I create a GDT or LDT, I cannot make the LLDT and LGDT to point to that, the GDTR and the LDTR to point to it. If I cannot make them point to it, then if I cannot access, suppose I create a descriptor table and I store it at 1000, right, and now I say in my ES5, that means I should take the 5th descriptor in my 1000, I cannot take it unless my descriptor table register points to 1000, and I cannot load 1000 into it unless I have privilege level 0. You are able to follow what I am trying to say? So, now we will next go, and this is something, again if you ask me a why, the answer is this is how Intel and AMD engineers found this. So, this is now your descriptor table. What will the descriptor table contain? Descriptors, correct? What will be each descriptor? As such I told you that descriptor will have 3 things as of now. What are those? The base address, the limit and the privilege levels, right. Now, it has much more here, let us now see. So, each descriptor is actually 8 bytes in size. You see there 0 to 31 in the bottom and 0 to 31 in the top. So, there are 8 bytes. So, the first byte, so if we say this descriptor starts at 1000, it will go from 1000, 1001, 1002, 1003, 1004, 1005, 1006, 1007. So, in that 7 bytes this descriptor itself will be stored. So, 1000, 1001, 1002, 1003 are the lower half. 1004, 1005, 1006, 1007 are the upper half, right, that is how it will be stored. So, the lower bytes, the lower 4 bytes of this 8 bytes are in the bottom and the upper 4 bytes are in the top. So, in the lower 4 bytes what will be stored? The first 16 bits of your limit and the first 16 bits of your base will be stored here. The first 16 bits of your limit and the first 16 bits of your base will be stored. In the upper half, the first 8 bits of your base will be stored in one corner, the remaining 8 bits will be stored in the other corner. It is a complicated instruction set architecture. We do not ask me why, there may be some reason, I can't find that reason, but this is how it is stored, right. So, this is how the designer felt it should be. Okay. So, there are 32 bits for the base, starting of any base address should be 32 bits. So, the first, that means 4 bytes, the first 4 bytes of the base is stored on the bottom upper half, another 1 byte on the upper in this part base 23:16 that you see on the top, and the remaining here. Okay. The limit, as I told you, is only 20 bits. So, I could have 1 MB segments, to start with, we can extend it to 4 GB, I will tell you later, but the 20 bits are stored as 16 bits in the bottom, and there is some small 16 to 19 in the top. You see seg limit 19:16. So, the 20 bits are accommodated like that. Then there are several bits. So, we have finished off segment limit, we have finished off base. Then please note that the 21st bit on the top is 0, always, it should be always 0. Okay. Why, I will tell you later. Then there are other type of bits that we will explain now. AVL, that is the 20th bit, it is available for use by system software. So, the operating system can use it for different purposes. It can color segments, etc. It can do a red black coloring of the segment. So many things are possible, but we will discuss something about this when we do the operating system course. But as of that, that is available. So, when the operating system is creating this, if it has no purpose for it, it can put any don't care, any 0 or 1 there, it does not matter. Then the next thing is D/B bit. Okay. So, this is default operand size. If it is 0, then it is 16 bit segment, 1, then it is a 32 bit segment. So, what happens is, why we have this? We have this because Intel and AMD had this legacy, had to support legacy. So, it has to support 16 bit code, because 86 was a 16 bit architecture, then we moved on to the 32 bit architecture. So, there is legacy. So, we have to support execution of the 16 bit code. So, if I have a 16 bit code, I go and make this D/B bit as 0, correct, then what will happen? 16 bit code will get, so all the code that I see there, all the operands I see will be treated as a 16 bit operand. If I make it 1, then it becomes a 32 bit operand. So, if I have a code that is compiled for 16 bit, then that code segment, that D/B bit should be made 0, then automatically it will start executing as a 16 bit. If I make it 1, it is 32 bit. Okay. So, that is the D/B bit. Now, there is a granularity bit, G bit. If I make it 0, then that limit 20 bits I have, right. Yesterday I explained in one of the session, the 20 bits, each entry, suppose I store in this 20 bits 1000, the limit is 1000 and my G bit is 1, right. Then what is this? It will be 1000 bytes. But if I store G bit as 1, then each entry is equivalent to 4 KB, right. So, if I put 1000 there and my G bit as 1, it becomes 4000 KB. You are getting this. So, the G bit will determine what each entry in the limit essentially means. What is the value, what is the weight of the entry in the limit. So, if my G bit is 0 and I put 1000, it essentially means 1000 bytes. If the G bit is 1 and I put 1000, then that 1000 essentially means 4000 kilobytes. So, by this I could get a segment which is 1 MB in size. I could also get a segment which is 4 GB in size, right, because the maximum limit I can put it as 2 power 20, and then I put the G bit 1, then it is 2 power 20 into 2 power 12, which essentially becomes 2 power 32, right. Then there is a segment limit. Then there is P bit, which is called the present bit. So, when I create a GDT, right, and I only fill up 3 or 4 columns, I fill 3 or 4 entries. What will be every entry? Every entry will be a combination of zeros and ones, correct, right. So, every entry can become a valid entry. So, somewhere I should say that this is a valid entry and this is an invalid entry, right, because if I create a GDT, I can store up to 255, we will see why. So, around 255 descriptors I can store, but I will not fill up all these 255 descriptors, I will fill up only 4 or 5 descriptors. The remaining all the descriptors would be will not be valid, but in the RAM I will have some random values there, and each can become a descriptor by it with that base and that limit, correct? Do you understand what I am saying? Yes or no? Now, so for that what we do, there is one bit called present bit. If that bit is 0, that means the segment is not present, that means that entry is invalid. If that bit is 1, then only that entry is valid. So once I create a GDT, the operating system creates a GDT or a LDT, it has to go through all these 255 entries and make the present bit 0 for all, so that no entry is filled, everything is invalid. Then it fills up one by one and makes the present bit 1. So any structure, so this is one principle of architecture. Any structure that you create in an architecture where it can be partially full, you need to have for every entry whether it is a valid entry or not, correct? Can you give me another example? Cache. If I create a cache, cache, it can be full, it can be half full. So there will be some entries, there will be some, so there is a present bit, valid bit and an invalid bit in a cache, for example. So like that we will have translation, look aside buffer, many things. All the things where it can be partially full, there should be one bit which essentially says which is valid or invalid, and this P bit tells that, okay. And there is an S bit which basically, there is a DPL which is the 13th and the 14th bit on the top, which gives you the descriptor privilege level. I told you, right, everybody will be given a privilege, the DPL gives you the privilege, and there are 4 privilege levels, so I can have 0, 1, 2 and 3. Then there is S bit which says that this descriptor belongs to a application or this descriptor is a system descriptor. So there is a classification, there are varieties of descriptor. What is a system descriptor, what is an application descriptor, we will see in great detail as we go. But as far as now, we have seen 3 types of descriptors already, a code segment descriptor, a data segment descriptor and stack segment. These are all belonging to the application. So for those descriptor, this S bit will be 1. When it is 0, it actually belongs to a system descriptor. Can you, so as we proceed, I will tell you many more about system descriptors, but just to tell you, the LDT, right, is a descriptor table that is described in the GDT. I as a process, I create the LDT by having an entry in the GDT which will point to an LDT. So the LDT itself is the describing of the LDT itself will come through an LDT descriptor, and that will be an example of a system descriptor, correct. So we will talk about that as we proceed in this session. And then there is a type, segment type, which is 4 bits in length. We will elaborate on the segment type also down the line. So every descriptor that is put on the descriptor table essentially has all these entries in that, okay. Okay. Now, how do we go and load these descriptors? I go and load this descriptor by a simple move statement, move ds comma 0x10. What does this mean? Yes, please answer. What move ds comma 0x10 means? It is 10. This is hexadecimal first, okay. 0x10 means 16. Move the value of 16 into the ds. If this is successful, then ds will point to the 16th descriptor in your descriptor table. It will point to the 16th descriptor in your descriptor table, correct. So now this move ds comma 0x10 is not just to go into ds and put the value 10. This is also very important from the security perspective. So this is all the architectural aid to security. So what does the architecture do here? The above command, namely move ds comma 0x10, is successful if and only if the descriptor stored at the offset 16, 0x10, 16 in the descriptor table, it has a privilege level numerically greater than or equal to the current privilege level. Now, how do I explain this statement? This is how the explanation goes. I am executing move ds comma 0x10. I am a process. I have some privilege level. What is my privilege level? What is my current, how is CPL defined? How is CPL defined? I am executing using a code segment, and that code segment has a privilege level, and that is my current privilege level. So, when I am executing, my code segment register should point to some code segment, right? From that only I can get that thing. That code segment will have a privilege level, and that is my current privilege level. Suppose my current privilege level is say 2, and now I say go and load the 16th descriptor in the descriptor table. That descriptor's privilege level is say 1, then I will be say stop, we can't do it. If that descriptor level is 2, I will be allowed. If that descriptor level is 3, I will be allowed. But if that descriptor level is 1 or descriptor level is 0, the architecture will give you a interrupt. It will catch and throw you to the operating system, saying this fellow is trying to do something which he should not do. You go and rectify the problem, right? This is the architectural aid to security, right? Right? So, if a process with current privilege level 3, that means I am executing through a code segment whose privilege level is 3, CPL is 3, I cannot load the segment descriptor of any privilege level, not CPL, any privilege level that is less than or equal to 2. Of any privilege level, descriptor privilege level which is less than or equal to 2, right, right, and so I cannot access the segment itself. So, if I am at privilege level 3, I can only access segments which are at privilege level 3. If I am at privilege level 2, I can only access segments which are at privilege level 2 and 3. If I am at privilege level 1, I can only access segments which are at privilege level 1, 2 and 3. So, this is how the whole thing works. Similarly, how do I create privilege level, how do I go and change the privilege? Now, I told you with this DS I can change DS, I can change ES, I can change SS, GS and FS using this move statement. But how will I change CS, right? There is no point in saying move CS comma something, then it will go and start executing from somewhere. So, the way I will change CS is by using either a jump statement or a call statement. For example, I can say jump 0x20 colon 0x1000. This is the way I change the CS, right. Currently I am executing some code segment, say let me say I am executing code segment 15. What is 15 in hexadecimal? 0xf, okay. Now I want to go to code segment 32, which is 0x20, right, hexadecimal 20 is 32, right. Now I say 0x20 colon 0x1000, essentially this means this will update the CS register to 0x20 and it will go and that 0x20 will be a descriptor, right, and that will have a base address. Let that base address be what? Let it be something, right. It can be say some 5000. Now you go and jump 0x1000, 0x1000 is what? 2 power 12, right, 0x1000 is what? Two power 12, each is 4 bits, 0x1000 is what? Find out what is it, okay. So, is it 2 power 12, correct, okay. So it will take you to 4096 plus 5000 which is 9096, okay, right. And this transition can happen only if 0x20 has a privilege level numerically greater than or equal to the current privilege level. So, if I am at privilege level 3, I can jump to 0x20 colon 1000, 0x1000 if and only if that descriptor that is stored in the 30-second entry also has privilege level 3. If I am at privilege level 2, I can do this jump only if the descriptor there has 2 or 3. If I am at privilege level 3 and the descriptor that is stored at 0x20 has privilege level 1, I can't do this jump. Okay. So, by this what we have ensured that I can go from a lower privilege level to a higher privilege level, numerically lower privilege level to a numerically higher privilege level. But how will I come from a numerically higher privilege level to a lower privilege level? I need to come for several reasons, right. I am a user program, I am doing printf. The printf will be at a numerically lower privilege level than the that will be in a higher privilege level than me in terms of power, numerically it will be lower than me. So, there are many reasons why I need to come to a lower privilege level, numerically lower privilege level from a numerically higher privilege level. So, for doing that there are certain mechanisms, and those mechanisms give you lot of ways by which you can protect. So, yesterday's stack smashing was a movement from a numerically higher privilege level to a lower privilege level without any check. Now, that type of a thing we can avoid because there are many ways by which the x86 architecture provides you ways by which you can stop a numerically higher level code to come to a numerically lower level code. If it has to come, then there are a lot of checks that you can impose, and by that you can do lot more protection in gain of privilege levels. Okay. So, this is another important aspect.